Hello everyone, welcome to Zero to Hero series, and today it's time for me to discuss the chapter electric potential, electrostatic potential and capacitance. So let's see who all are here and what are you all saying. So as you know that in this series we are basically discussing all the important chapters, and not only that, we are also discussing the concepts of the chapter for your PUC as well as KCET. So if you are someone who is wondering how can I prepare parallelly for KCET and PUC, then don't worry, we are going to discuss everything in this series. And this is the second chapter of physics, electrostatic potential and capacitance, and we will see the importance of the chapter in terms of PUC and what are all the questions and what is the blueprint. Everything will be discussed in this lecture. So first let us see the high weightage topic of this chapter. So high weightage topic of the chapter: electric potential due to a point charge, potential energies application, equipotential surface, polar and non-polar molecules, potential energy of a system of charge, capacitors in series and parallel plate capacitor, relationship between electric field and potential energy of a dipole in an external field. So these are all the things that we are going to cover in this lecture, maybe not in the same order, but definitely we are going to cover everything. Now if you see the PUC weightage of the chapter, PUC weightage of the chapter is 1 marker, 1 2 marker, 1 3 marker, 1 5 marker. So total weightage of the chapter is 11 marks. Also in KCET, if you see that on an average 2 to 3 questions is coming, some cases 4 questions also came. In our expectation is that 3 questions will come from this chapter in 2026. That is our expectation. So 3 questions you can guarantee if you watch this lecture completely, right? So also we have done a PUC analysis of the chapter. So if you see what are all the topics that is being coming repeatedly in PUC exam: electric potential due to a point charge. Even though this is a very important derivation, it only came once in 2025. It did not came before that. Okay, so this is one of the very high Ashia Bhagava, hi. And welcome to the lecture. So electric potential due to a point charge, even though it's a very important derivation, it came only in 2025. Previously it has not come, so only once it has came. Potential energy application based on numerical questions or other potential energy related questions, that came 3 times. Now equipotential surface, it came only twice. Polar and non-polar molecule, it came also twice. Potential energy of a system of charge based question, conceptual question, came once. Capacitors in series and parallel based question came once. Parallel plate capacitor, the expression for parallel plate capacitor has came 4 times. Also relation between electric field and voltage, the derivation E is equal to dV by dx, that came 3 times as well, right? Okay, now so if you have any other doubt, don't forget to post that in the chat. I will be active on chat, so don't forget to ask your doubts in the chat. Now let's start with the chapter. So first concept we are going to discuss is electric potential energy. It is similar to that electric field chapter, where we started with electric force, then we moved on to electric field, then we came back to electric force in terms of electric field. Similarly, we will start with electric potential energy, then from there on we will move towards electric potential, and then after electric potential is discussed, we will revisit electric potential energy once again. Right? Now let's see what is electric potential energy. So electric potential energy is basically defined as the work done to move a charge, okay, work done to move a charge inside an electric field. Okay, so here F external expresses that the force that you are applying to move a charge in the presence of another charge. Okay, so there is a presence of one charge. Here we have this is called a test charge, which you are moving, say, from point A to point B, and whatever work that is being done, this is called electric potential energy. And what is the unit of energy? Unit of energy is same as your mechanical work done, that is joules. Okay, so the same unit is applicable for electric potential energy as well, so its unit is joules. Okay, this work is against the electrostatic force and gets stored as potential energy. So when you do some work in an external electric field, the work is not lost, it is basically stored. That's why electric field is sometimes called conservative force. Okay, conservative force field, conservative field, because the work that you are doing is not lost, it is basically stored in the system. Now if you are not doing any work, system is doing any work, that means electric potential energy is negative, because the stored energy is being spent. So when the stored energy is spent, that means the work done will be negative. So electric potential energy can be negative as well. The work done by the external force increases its potential energy by an amount equal to potential energy difference between points A and B. Thus, the potential energy difference can be written as delta U equals to UB minus UA equals to WAB. So the energy difference is being calculated using this formula. Okay, so remember, and most of the cases the individual potential energy is not important, rather than the energy difference is important. So energy difference is same as work done. These are the basic of this chapter. So if you understand this, work done is related to potential energy, then most of your life is sorted, right? Now electric potential, let us look into something else. Electrostatic potential. Now we are moving in from potential energy towards electrostatic potential. What is the meaning of this? So electrostatic potential is basically potential energy per unit test charge. So if you make the same charge that you have used in the last case, if this charge is made equals to 1, then you get potential, okay. So for potential, the charge is equals to 1, that's it. If you can make the charge equals to 1, then you get potential. Potential is different than that of potential energy. Potential is represented by the unit volt, and it is nothing but joules per coulomb. Okay, volt is nothing but joules per coulomb, and because we use this unit a lot, that's why it is mentioned as volt. Okay, and delta V, the change in potential, is given by delta U by Q. Work done in an external force in bringing a unit positive charge from infinity to a point is the electrostatic potential V at that point. This is the definition of electrostatic potential, and sometimes it is asked as write the what is electric potential, define electric potential as a part of a long 5-mark question. So you have to remember this definition as well. So the work done to bring a unit positive charge from infinity to a point in space in an electric field, obviously, is called electric potential of that particular point. Okay, now potential due to a point charge, this derivation is important for your PUC. So here we have a charge capital Q, and we are trying to measure the electric potential at this point P. So this is the point where we want to find the potential. Okay, so how to do that? The derivation I will do it briefly. So for that you have to take you have to extend this line and take 2 points A and B. Okay, two very close points, two friends A and B, and extend this line up to infinity. Okay, don't draw it like that, you have to draw it slightly more accurately. Okay, anyway, so what you have to show that, suppose the distance between A and B is very small, which is given by dx. Okay, why we are doing it, that also I will explain. That's the student don't understand the derivation, they try to memorize everything and they forget it. Okay, so I will explain why we are doing it. So this distance of the point A, say A is x. The distance of A and B almost x. Now you have taken a test charge plus 1. Okay, you have taken a test charge plus 1, which is located at infinity, and you are trying to bring it to this point P. That is our destination, right? The definition says that you take a unit positive charge, okay? You take a unit positive charge and slowly bring it towards the point P, very slowly. The point is being, as you are moving the test charge from infinity towards this point, the electrostatic force that is acting on this charge will also change. At infinity, electrostatic force is 0, right? That is the definition of force, because force you can say k q1 q2 by r square. Now r is infinity, means 1 by infinity square. 1 by infinity square means force is 0. That's why infinity is important. Why infinity is important? Because at infinity force becomes 0. Now when you are bringing this test charge, okay, you cannot handle infinity. First of all, infinity is very difficult to manage. If you are trying to manage infinity, it can get very, very difficult if you try to do anything with infinity. Okay, infinity obviously is something very large number. So what we have to do, we cannot tackle infinity, so we have to use some finite points which is known to us. That's why we are choosing these 2 points A and B. Now why we are choosing these 2 points? Because we have to formulate an equation, and work done equation. What is work done? Work done we know is given by F external, okay, times the distance that you are displacing. Now why this distance has to be very small and why it has to be dx? Because this external force has to be same as the electrostatic force that is acting on the charge. If it is slightly more or slightly fast, then it will start accelerating. If it is lower than that, it will not move at all. Okay, so we don't want acceleration, we want exactly the same electrostatic force that is acting at this point. And electrostatic force actually changes with distance. Electrostatic force changes with distance. So if you change the distance, if you take this dx too large, the electrostatic force between these 2 points will vary a lot. So you cannot use the integration formula. Just to apply the integration formula, which is bounded by the mathematical form, which says that this has to be fixed. You cannot change it. That means at this particular point it has to be constant. So between B and A, when you are bringing the test charge from B to A, the force that is acting on this charge should be constant. That's why we are choosing a very small distance and assuming that even during this small distance force is almost same. Now what is the force that is acting on this? The force acting on this is given by K capital Q into small q, which is 1 in this case, divided by x square. This is the internal force. This is internal force, or the force by the charge. By the charge. Right. Now what I said, you have to apply external force which is exactly equals to this force. The external force has to be exactly equals to this force, but in the opposite direction. External force has to be exactly equals to, suppose this is positive charge, this is also positive charge, then there will be a repulsive force which is acting in this direction. You have to apply an external force in the opposite direction, so that this is the internal force, this is the external force, which is exactly same but in opposite direction. So the external force has to be negative. So do not forget this negative sign, and do not forget to write both forces. This is internal force, this is external force. Okay, so that force will also be same but with a negative sign, kq by x square. So now we can write our integration to move the charge from B to A small work is being done. So small work done we will write in terms of dW. So small work done is given by F external into dx. Now to calculate the total work done to bring the test charge from infinity to our known point P, which is at a distance smaller away, okay, what we have to do? We have to integrate this. So how to integrate? So we have to integrate both sides. So dW, starting point is infinity, ending point is R. This is the total work done, and that total work done we will say W, and that will be given by infinity to R F external into dx. Now we have formulated an integration. So if you formulate this integration, you have to just simply solve it. So integration, work done equals to integration infinity till R. Okay, F external force we have calculated, this is the external force, minus kq by x square into dx. Now k and q are constant, k is Coulomb constant, q is particularly for single charge, it is constant. So minus kq is common, and we get integration infinity till R dx by x square. So dx by x square is a very simple, easy integration. So work done W equals to minus kq into integration infinity till R. Okay, so dx by x square means obviously minus 1 by x. That is the integration. So once integration is done, so this is a definite integration. So what you have to do, you have to write it like this, infinity to R. Now minus is common, so we get kq, minus can be taken common, and minus will be plus. So this will become plus, and we have 1 by x infinity to R. Now what is the meaning of this kq? So first you have to put the upper limit, which is R, 1 by R, minus 1 by the lower limit. So we have to replace the x once by upper limit, once by lower limit. Those who don't know or forget definite integration. Okay, so 1 by infinity is basically 0. 1 upon infinity is 0, 1 by 0 is infinity, so 1 by infinity is 0. So we get this as kq by R. This is the work done. Now this work done by definition is the potential of this point. So we get this expression, and you have to write the value of k over here, 1 by 4 pi epsilon naught, and here you can take this as capital Q. Okay, so capital Q by R is the expression for electric potential. So this derivation is very important. Sir, how to start preparing for KCET from beginning? Gladwin-Shalom. So Gladwin-Shalom, we have already started this 0 to hero series. One lecture is already live and it's completed. You go and check that out. Also follow this lecture because here we are discussing everything from basic, from starting. That is why our series name is 0 to hero. Right, so we are starting from scratch, everything from scratch. Even we are considering all the PUC important topics as well, so that you don't feel left behind. PUC is also important for your KCET preparation. Remember that 50% of your weightage of KCET is coming from PUC, so don't ignore PUC. KCET is obviously you have to prepare, so whenever you are studying, try to combine both KCET preparation as well as PUC preparation. Okay, so when you plot this graph of electric potential versus distance, you get this kind of equation graph. Okay, so this is the graph of electric potential versus distance. Also for reference, electric field is also being plotted over here. So if you see that voltage starts at very lower value compared to electric field and goes slowly towards 0, whereas electric field, it starts higher but it goes to 0 very quickly. So electric field and potential, one is varies upon 1 by R square, one varies upon 1 by R, and both when it is touching 0 are going obviously shoot up almost infinity. Okay, but comparatively electric field is slightly bigger compared to voltage. They becomes equal at some point, and then electric field falls to 0 faster. Electric potential on the other hand, initially it is smaller, but slowly it takes over electric field and goes to 0 again, but slightly slower compared to electric field. Okay, now let's see potential due to a dipole. Potential due to a dipole. Yes, welcome Gladwin. You should follow our lectures more regularly, because in our lectures we are trying to cover as basic as possible, and if you have any doubts, don't forget to mention in the chat below, in the live chat, so that I can answer all of your queries. Okay, so maybe it is subject related, maybe it is general queries. Don't forget to mention in the chat so that I can read and I can answer. Right, now here we are basically not going to derive this electric potential due to a dipole. The derivation is not important for your PUC. It never came in the final board exam, almost never in the last 5 to 6 years, the papers that we have checked. It did not came once, even in the second paper or third paper also it did not came once. So you can skip the derivation, but this formula is important for KCET. The electric potential due to a dipole, it is important for your PUC. Last lecture, while discussing, I gave the formula to you. So you should remember this formula, because based on this formula, one very simple part is the potential for a dipole varies as 1 by r square. Okay? And if you go back to our previous derivation, if you see that here potential varies as 1 upon r. So normally electric potential due to a point charge varies as 1 by r, whereas potential due to a dipole varies as 1 by r square. So if you remember, electric field due to a dipole, be it axial or equipotential, okay, if it is dipole, it always varies as 1 by r cube. So based on that also we have seen questions in your KCET exam. So very easy. Now it might come as an MCQ for your PUC exam as well. So let's see few questions of your KCET for last, let's see. So this questions came in 2025 also based on this concept. Now potential at a point A is minus 3 volt, and that at another point B is 5 volt. What is the work done in carrying a charge of 5 millicoulomb from B to A? So very important, interesting question. So here we have point A and point B. The distance between them is not given. What is given is that the potential at A is minus 3 volt. Potential at B is 5 volt, and they are asking what is the work done in carrying a charge of 5 millicoulomb from, so 5 millicoulomb from B to A. So you are carrying the charge from B to A. What is the work done? Quickly answer this question. Now how to calculate work done? So we know that work done due to a unit positive charge. Work done, if it was given as simply 1 coulomb, then it is simple. Then you have to just simply calculate the potential difference. Basically potential difference, that is final point minus initial point. Potential difference is always calculated final minus initial. Final potential difference is always final minus initial. Okay, remember this, potential difference is always final minus initial. Does not matter whatever is the sign, it is always final minus initial. Now work done, because it is not given in terms of 1 coulomb, it is given 5 millicoulomb. So work done will be Q into voltage. Okay, charge into voltage will be charge into potential, basically will give you the work done. So how to calculate that? 5 millicoulomb means 5 into 10 to the power of minus 3. And what is the VA? VA is minus 3. And what is B? B is 5. So minus 3 minus 5. So you get minus 8 into 5 into 10 to the power of minus 3. Okay, so it will be minus 40 into 10 to the power of minus 3, or minus 0.40 joules. So work done is minus 4.0 for minus 4.40 joules. So correct answer is option A. Okay, 10 to the power of minus 3 means you have to shift it 3 times. Okay, 1, 2 and 1 more 3. That's why it is 0.4. Okay. or no, sorry, 3 times, no, so it will be 0.040. Okay, so 3 decimals you have to move it, so it will be 0.040. So correct answer is not A but option D. Correct answer is option D. Okay, now next question. The electric field and potential of an electric dipole along its axis vary with distance small r respectively as. So as you can see, this question came in 2023. Last one is 25 and this one is 2020. Yes, Gladwin, you are correct. Now answer this question. Question number 2, easy question. I just discussed the answer in previous just few minutes back. Now try to answer this question. Electric field and potential of an electric dipole along its axis vary with the distance as respectively. So how does electric field and potential vary? So first is electric field. First one is electric field, second one is potential. First one is electric field, second one is potential, and we are asking about dipole. Okay, Aisha is saying option A. Gladwin is saying option D, then he changed to option A. So remember, what about first is electric field? Electric field varies as 1 upon r cube, whereas potential varies as 1 upon r square. So order is very, very important. Okay, even though both terms are correct, but the order is wrong here. The order is important. First one will be 1 upon r cube, second one will be 1 upon r square. So it is neither A nor D, it is option C. Okay, order of the question. So whenever you answer a question, KCET, remember that ratio based question or respectively based question. Okay, respectively, here it is mentioned respectively. Respectively means first one will come first, so electric field will be first, electric potential will be next. So respectively and ratio, find the ratio. So there will be options such that they will give you wrong order as well. So wrong order, even though the answer is correct, okay, order is wrong, that means if you mark option A, you will get 0 marks. KCET, there is no negative marking, but still you will not getting the marks. It's an easy question. So if the question is easy, take extra 2 seconds to make sure that your answer is correct. Okay, don't make hurry. So this answer is option C, not option A, because the order is electric field and potential. So this is electric field, this is potential. Okay, now answer this question. The electrostatic potential due to an electric dipole at a point in the equatorial plane is. Very interesting question. So electrostatic potential due to an electric dipole at a point. We are not talking about electric field, we are talking about potential. Okay, electrostatic potential at the axis of a dipole. Equatorial plane of a dipole. Equatorial plane means this axis. What is the potential? Good evening, Pradyum. You are slightly late. We have started. Now answer this question, everyone. Question number 3. Very interesting question. 0, 1 by 4 pi epsilon naught p cos theta by r square, 1 by epsilon naught p cos theta by, I think there is slightly mistakes. All options are given same. So this will be r square and this will be r cube. Okay. R square, r cube. Which option is correct? Gladwin is saying option A. Why 0? Can you briefly say? So if you see that electric potential is not a vector quantity, first of all. So electric field, in case of electric field, when we calculated electric field, we got 2 different directions and we added them to calculate the electric direction of electric field. But here electrostatic potential, first of all, it's a scalar quantity. Electrostatic potential is a scalar quantity, so you do not need to consider the direction, only the value is important, and in case of electrostatic potential you have to take the sign of the charges as well. So those who have watched my previous lecture, I said in case of electric field you should not consider the sign of the charge, direction you have to consider, but in case of electric potential you have to consider the sign of the charges. That is very, very important. So here it is, suppose the distance is same. So if any point is located on equatorial plane, all points are at same distance. Okay, all points. So if you consider the distance from this side, say R1, this will also be the same distance R1. Okay, so the distance of this point from positive and negative, every point, each and every point, this will be satisfied. Distance from each charge will be same. So this will be plus V, this will be minus V because the charge is negative. So that's why plus V minus V, the potential will be 0. So the potential on the equatorial plane will always be 0 no matter what, okay, on the equatorial plane. In any other point, the answer will be 1 by 4 pi epsilon naught P cos theta by R square. Name the physical quantity whose SI unit is joules per coulomb. Name the physical quantity whose SI unit is joules per coulomb, power, electric field, electric potential, dipole moment. Answer this now. C. Everyone is saying C. Yes. So electric potential is work done per charge, that is joules per coulomb. I already mentioned. So if you are following my lecture, you should know this. Now, before I continue, just wanted to remind you that ABHYAS KCET test series is live, and if you want to take part in it, definitely you should consider it. Also, you want to practice more questions in a timed manner, then definitely you should consider 35 KCET tests are there. 4 are free and 31 are paid. So you can register yourself through the link given in the description section of this video. You can register yourself and get the 4 free test papers. It may not appear directly immediately, it will take some time, but you have to access the papers via our app only. Okay, Deeksha Vedantu app. You have to download the app, or you can use our web page as well, but it will not come as a simple PDF, downloadable PDF. You have to access it through our app or website only. Okay, and you will also get free, absolutely free of cost, chapter wise KCET PYQs, the PYQs that we are solving in this lecture and all other lectures. Everything you will get as a practice. Also you will get real KCET exam pattern and timing, which is very, very important. So if you want to practice how to solve 60 questions in 60 minutes, then definitely this is the way to start. Okay, also all PCM as well as biology, those who want biology, that is also covered in this part, and the price is 1499. Right, let's continue. Potential energy in an external field. So as I mentioned, we will start with potential energy, move towards potential, and then we will come back to potential energy in an external field. So electric dipole, when an electric dipole is placed in an external field, its potential energy is given by minus PE cos theta, or it can also be written as minus P dot E. Okay, one small mistake over here, this will be small p. Okay, P refers to dipole moment. P is dipole moment. Okay, and E is external electric field. So when you keep an dipole in an external electric field, apart from the torque that is acting on it, there will be a potential energy as well. The potential energy of the dipole is given by minus PE cos theta. Now, where the potential energy be minimum? Potential energy is minimum when theta is not 90 degrees, by the way, when theta is equals to 0 degrees. Okay, potential energy is minimum when theta is 0 degrees, not at theta 90. Why? Because theta 90, okay, u is 0, but that is not minimum, because the minimum value is -1. If you put cos theta equals to 0 over here, you will get cos theta is 1. Theta 0 means cos theta 1, that means -1 into p, minus p, basically you will get minus p. So negative value is smaller than 0. Negative value is smaller than 0, that means this is the minimum value. Many students make mistakes. Whenever they were asked what is the minimum value of potential energy, they mark theta 90 degrees. Okay, theta 90 is u is equals to 0. U is equals to 0 at theta equals to 90 degrees, but this is not the minimum value. Also, this one important point is that if the potential energy is minimum, then we say that the dipole is in stable condition. This is a stable condition. Okay, stable equilibrium. And if you put theta equals to 180 degrees, very interestingly, the potential energy is maximum, which is equals to plus p. Okay, plus p. This is also equilibrium. This is also equilibrium, but it is unstable equilibrium. Okay, so theta equals to 180 degree, the dipole is in unstable equilibrium. Theta equals to 0 degree, dipole is in stable equilibrium. Any other point, the dipole is completely unstable. Any other point, including theta equals to 90, the dipole is unstable. Okay, now not in equilibrium. Equipotential surface, very very important concept from this chapter. Based on this, we have seen MCQs, we have seen questions coming, properties of equipotential surface, right? Sir, is the derivation important for u is equal to p cos theta? Pradyum, I have not seen that derivation, but based on that, questions will come in KCET. The derivation may not be that important. The more important derivation is tau equals to p cross e. That is more important, not p minus p cos theta. Okay, p cos theta may be coming, but not important. Okay, according to my experience, it has not came in last 4-5 years, but obviously the formula is important. If a numerical question is coming from this chapter, that is not we cannot predict it right away, so that formula might be handy for you. Okay, but derivation wise, that is not important. Tau equals to p cross e is important. An equipotential surface is a surface with a constant value of potential. So equipotential surface is a surface with a constant value of potential at all points on the surface. Okay, so if you see a point charge, very common charge, point charge, if you consider a point charge, you will see that if the distance is constant from the point charge, what is the formula for potential? Formula for potential due to a point charge is kq by r square, r not r square, sorry, kq by r. So if you keep this r constant, okay, the potential value will be same. So for a point charge, if you can construct a spherical surface, okay, all points on this sphere, will be at same distance. Okay, the distance of this point, this point, this point, and this point, all points on this sphere will be at equal distance. So that means the potential on the surface of this sphere will be constant. So we say this is an equipotential surface. Similarly, if you take a larger sphere, okay, if you take a larger sphere, all points on this sphere also are at equal distance. Okay, so the potential on this large surface will also be same. So we say that the equipotential surfaces for a point charge is concentric spheres. This is concentric spheres, right? They are all concentric spheres. Now, if you consider this surface and this surface, even though both of them are equipotential surfaces, their relative distances are not equal. So even though these two are equipotential surfaces, the potential on this point is not same as this point, but potential on this point is same as this point, but potential at this point is not same as this point. Two equipotential surfaces, different equipotential surfaces will have different potentials, but points on the same equipotential surface will have the same potential. Okay, let's move on. For any charge configuration, equipotential surface through the point is normal to the electric field at that point. So what is the meaning of that? Suppose I want to find the direction of electric field. So I want to find the electric field at this point. So electric field will be normal to the surface. Normal to the surface means if you draw a tangent over here, okay, this will be normal to the surface. The angle will be always 90 degrees. Electric field will always be normal. So basically if you join this point and this center of this charge, you will get this as passing through the, it will be always normal to the surface. Okay, so equipotential surface, if unknown equipotential surface is given to you, suppose an equipotential surface is given to you like this, and they ask what is the direction of electric field, it will always be normal to the surface and angle will always be 90 degrees. Okay, so here is another example. Here we have parallel equipotential surface, electric field is moving from left to right, okay, and all electric fields are actually normal to each and every surface. Now another important, this derivation is important, electric field, relationship between electric field and potential. Here you have to use this diagram. Now remember that in your textbook they have used V plus delta V. I am using V minus delta V, which is easier, okay, to remember, and the mistakes the student makes, they don't get this negative sign, which is not correct. So that's why always use V minus delta V, and these two are two equipotential surfaces, two different equipotential surfaces. That means potential at each and every point on this surface is equals to V. Potential at each and every point on this surface is V minus delta V. The distance between these two equipotential surfaces is small, which is given by delta L. Now if you take a small charge, say small q, and if you want to move this small q charge from this point A to B, then what is the work done that you have to do? The work that you have to do is given by, the work done is given by, what is the formula? The charge times difference in potential. Now how to calculate the difference in potential? As I mentioned, final minus initial, always final. Here final is V minus delta V and initial was V. Okay, so this is the work done to move a charge from A to B, A to P. Okay, so here you get the work done is Q into delta V. There is a negative sign over here. Okay, if you just simplify it, you will get minus Q into delta V. That is the work done to move the test charge from A to P. Now what is the definition of electric potential? Definition of electric potential states that work done divided by the charge is actually the potential, or in this case it is minus delta V. Anyway, we'll come to that, but let us do one more thing. The work done can also be calculated in terms of force. So what is the work done in terms of force? Work done in terms of force can be written as force into displacement. Here displacement is the small delta L. Now we are assuming that the distance is small so that the force is constant. So what is the electrostatic force? Electrostatic force is given by Q into E. Okay, we studied in our last chapter, right? Force, electrostatic force in an external electric field is given by Q into E. Q into E is the electrostatic force. Now that into delta L is the work done. Now we have to use this formula over here. So instead of work done, we will put this Q into E into delta L, that is minus Q into delta V. So Q cancels, we get E equals to minus delta V by delta L. This is the derivation for your PUC exam. Very simple, easy, but you have to write everything, and in case of this delta L tends to 0, if you take limit, delta L tends to 0, this becomes minus dV by dL. This formula is important for your KCET exam. They will give you a voltage and they might ask you calculate electric field, or if they give you electric field, they ask you to calculate electric potential. Then what you have to do, you just simply have to calculate potential by dV equals to minus E into dL and then integrate. So you can calculate potential as well from this formula. This is slightly higher level. Generally JEE level questions might come like this, but in KCET this direct formula based question might come. Electric field is in the direction in which the potential decreases the steepest. Okay, electric field. Now if I say that electric field is in the direction, what is the direction of electric field? Is it in this direction, or in this direction, or in this direction? There are multiple possible direction of electric field. So it says no, it cannot be in any random direction. It is the steepest where the electric potential is decreasing steepest. Steepest means it is decreasing very fast. If you go in this direction, electric field will not decrease as fast as it is decreasing in this direction. Okay, so these are not the direction of electric field. Electric field is this in this direction. So basically remember that electric field is in the direction where the electric potential decreases the steepest. Okay, what else? Electric field is normal to the equipotential surface at the point. Electric field is normal to the surface at this point, so this is also normal. Okay, this angle is 90 degrees. Now let us look into the potential energy in the external electric field. Potential energy in the external electric field. Single charge, very important. We have only one charge. The electric field is their external electric field. So here we have external electric field like this. Okay, and you have a single charge. What is the potential energy of this charge? When a charge small q is placed in an external electric field, the potential energy of the charge is given by U equals to Q into V. Here V is electric potential at that point. So if we know the potential at this point, we can find the potential energy as well. Potential energy is Q into V. Now we have not one charge but two charges. So this is Q1. Now we have another charge Q2. So suppose the voltage is 1 here, voltage is 2 here. Now what will be the potential? When two charges Q1 and Q2 are placed in an external electric field, the potential energy due to the system is given by, now here, so instead of 1 and 2 they have used this symbol P and Q. Okay, this is say P, this is say Q. Now Q1 into Vp, Q2 into Vq, that is fine, that is same as this principle. So two different potentials, you are adding them. But not only that, because there are two charges, there will be an electric potential between these two charges as well. Remember this, because there is an external electric field, individual potential of this charge is Q into its potential. Individual potential of this charge is again its Q into its potential. So these are the individual components. But because there are two charges, okay, the total potential will be 1 by 4 pi epsilon naught Q1 Q2 by R as well. This is the potential of the entire system. Now if only two charges are present, no external field, if this and this are 0, then potential energy of two charges is given by K Q1 Q2 by R. Remember this formula, this is important for KCET question. Okay, based on this we might get one small numerical question. Clear? Any doubt? Please don't forget to mention that in the chat below. Right? Now we will move into slightly trickier term. This is specifically for KCET. Now we have three charges. External field is not there. Only three charges are there. Okay, Q1, Q2, Q3. Okay, Q1, Q2, Q3, the distances between them are R12, R23 and R13. So what will be the potential energy of this three system of charges? The potential energy will be 1 by 4 pi epsilon naught, which is common. Q1 Q2 by R12, Q1 Q3 by R13, Q2 Q3 by R23. So you take two charges, any two charges, multiply them, divide by the distance between them. Similarly, you take another two charges and divide them by the distance between them. Lastly, take the other last two charges and divide them by the distance between them. Okay, remember this very easy formula, but don't make mistakes. Also, it does not matter when the three charges are here. Okay, this formula is important for your PUC exam in terms of numerical question, not in terms of theory. Obviously derivation will not come, but in terms of numerical question, this formula might be important in your PUC exam as well. Now this potential energy that we have calculated is independent of the order of these charges. It does not matter which charge you have brought first. Okay, it is independent of the order of the charges on which you are bringing in. Okay, the final expression of U is independent the way the configuration is assembled. Basically there are three charges. Okay, you can take Q1 first, or you can take Q2 first, or someone say no, I want Q3 first here, then I want Q1, then I want Q2. Someone says no, I will bring Q2 first, then I will bring Q1, and lastly I will bring Q3. Okay, it does not matter the way this system is assembled. It only depends on the mutual distances and the values of the charges. Okay, and not the way the state is achieved. As I mentioned, this is path independent. This, in short, this is path independent. Okay, these are the all properties of conservative field, path independent. Okay, let's see a few questions. Which of the following statement is not true? Which of the following statement is not true? This is also a very tricky question. Not true questions are also tricky. That means here will be three options which will be correct, only one will be not incorrect. Equipotential surfaces are the surfaces where the potential is constant. Equipotential surfaces for an uniform electric field are parallel and equidistant from each other. Electric field is always perpendicular to an equipotential surfaces. Work done to move a charge on an equipotential surface is not zero. Which statement is incorrect? Answer quickly. Let me have a sip of water. Gladwin is saying option D. Yes. So work done to move, remaining all A, B, C are correct. Okay, A is correct, B is correct, C is correct. So when you are moving a charge in an equipotential surface, okay, both points have same potential. Both points have same potential. So what is the work done? Work done is charge times difference in potential. Charge times difference in potential. Now difference in potential is zero over here. That's why the work done to move a charge in an equipotential surface is zero. Now this is a slightly tricky question, but not super difficult in terms of mathematics. Try to answer this question as well. The figure gives the electric potential V as a function of distance through four regions on x-axis. Which of the following is true for the magnitude of the electric field E in this region? So here we have four regions A, B, C, D. Okay, for each region they are asking you what is the relationship of the electric field. Even though this is asking about electric field, this is a electric potential question because the graph is given in terms of volt versus distance. Okay, so what concept we have to use? We have to use this concept. E equals to minus, or magnitude they have asked. So magnitude means you do not need to use the negative sign, only remember dV by dx. So only remember this formula, and if you remember this formula you can answer this question. Let me go out of the screen so that you can answer this question. Yes, Pradyum, 5D is correct. Answer question number 6 now. Gladwin is saying option D, EA equals to EC and EB is less than ED. Okay, let's see, let's check. Let's check. So if you see that in this region electric potential is constant, is constant at 2 volt. Okay, if you see this one, this is also constant, it is constant at 4 volt. So dV is 0 for both cases, dV equals to 0, dV equals to 0. Change in potential when it is going from 2 to 4, that is region C, okay, dVs are 0 for these two cases. So if dVs are 0, that means electric field is 0. So electric field here it is 0, so EA equals to 0 and EB is also equals to 0. Okay, so if dV equals to 0, then electric field is also 0. So that means EA equals to EB, both are 0. EA equals to EB equals to 0. Now what about these two regions? So if you see that here dV is changing from 2 to 4. So change in dV is 2. So here it is changing from 2 to 4, that means change in dV is 2. But when you are considering this point, dV is changing from 4 to 0. So initially it was 4, suddenly it goes to 0, so here dV is equals to 4. Okay, in terms of distances, all the distances are same. This is 1, this is 1, this is 1. This distance is actually not same, this distance is 2, but because dV is 0 does not matter. Here also distance is 1. So distance is 1 for this and this, so dx is same for both B and D, but dV is different, dV is more for region D, so ED is definitely greater than EB. Okay, so we can say that which option is correct. EA equals to EC, EA equals to EC, okay, EA equals to EC, not B, sorry. EA equals to EC and ED is greater than EB, so obviously option D is correct. Yes, you are correct. Yes, yes, Gladwin. Hi, ban kafi hai. I don't understand. Yes, correct. Option D is correct. Yes, yes, I corrected the mistake. Right? Now let's move on. Equipotential surfaces for an isolated point charge are dash in shape, spherical, planar, cylindrical or conical. So equipotential surfaces for an isolated point charge are dash in shape. So what is the shape of equipotential surface for a point charge? Answer quickly. Spherical, yes, yes, spherical, yes, option A. So equipotential surface for an isolated charge, they are all spherical. Okay, not circular. Circular could have been a good option. Yes, now answer this. An electric dipole is placed in an uniform electric field. The dipole moment makes an angle theta with the electric field. For what angle theta is the potential energy of the dipole is maximum? So I have discussed it in my lecture. So if you have listened to it, you can answer this. The angle is given by theta. This is dipole moment. Okay, so this is negative, this is positive, and this is the electric field. So for which angle theta the potential energy is maximum? For which angle potential energy is maximum? 0, 45, 90, 180. He is very fast in answering. Someone else, if anyone wants to answer. Yes, theta equals to 180 degree, the potential energy is maximum. Okay, remember there is a negative sign. There is a negative sign PE cos theta. So because of this negative sign, the maximum value is at 180 degrees, not at 0 degrees. Now, next, electrostatics of conductors. Few points that you have to remember. Metallic conductors contains mobile charge carriers, namely obviously electrons, right? In a metal, the outer valence electrons are part away their atoms and are free to move. Obviously, we know that in a so far we have already studied the band structure. Here we have a valence band, we have a conduction band on top of that. For metals, conduction band and valence band, they overlap on each other, and electrons can move from valence band to conduction band. So in metal, outer valence electrons part away from their atoms and are free to move. These electrons are free within the metal but not free to leave the metal. The free electrons form a kind of gas. They collide with each other and with the ions and move randomly in different directions. In an external electric field, they drift against the direction of the electric field. So these are all the common points that we know about conductors. But I'm extremely sorry, I have to take 2 minutes break because some emergency has occurred, but I will give you 2 questions to solve these 2 questions, and I will be back in 2 minutes. Sorry guys, our editor requires a small help, that's why I had to go. So Gladwin is saying 11D and Pradyum is saying 11C, 12A. Okay, questions are very easy. I will come back to these answers just in a second. Okay, let me complete this, then I will come back. Okay, it's not very difficult, by the way. Let's see, I will come back, don't worry. So this part is done. Now electrostatic conductors, we are discussing about electrostatics of conductors. So these are the very important points. Each and every point is a potential MCQ question. Inside a conductor, electrostatic field is 0. Okay, so if you consider an electric conductor, so when an electric field is applied across the conductor, there is a exactly equal internal electric field is developed inside the conductor, and these two electric fields actually cancel each other. Okay, because of this cancellation, electric field inside the conductor is 0. Inside the electric field, inside the electric conductor, electric field will always be 0 whether an external electric field is present or not. Now, at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. So if you are considering a charged conductor, okay, charges will always reside on the surface of the conductor. Charges will always reside on the surface of the conductor, and electric field is normal to the surface at each and every point. No matter which point you take, it is always normal. Okay. In the interior of a conductor can have no excess charge in the static situation. Any excess charge must reside on the surface. Okay, well-known point. Electrostatic potential is constant throughout the volume of conductor and has the same value as inside on the surface. So electrostatic field inside the conductor is always constant, and it is constant from center till the surface. After you cross the surface, electrostatic potential starts to decrease. So electric potential inside a conductor is constant, electric field is 0. Okay, electric field at the surface of a conductor, of a charged conductor, is given by E is equal to sigma by epsilon naught n cap. This is constant. If you know the surface charge density, you can calculate the electric field at the surface of a charged conductor. Okay, sigma by epsilon naught. Now, electrostatic shielding. This is very, very important. Based on this, we have seen some questions in the past as well. Electric field inside a cavity of a conductor is 0. So if you, even if electric field is 0 on the here as well, electric field is 0. And not only that, if you have a cavity, cavity means a gap. Okay, like we have cavity in our teeth. Similarly, cavity inside a conductor will have potential 0 as well as electric field is 0. Potential is constant, but electric field is 0. Potential is constant, same as inside the conductor, but electric field will be 0. Electric field will be 0 not only in the conductor but also inside the cavity. Why it is important? This is used to protect high value equipments. Okay, for example, an MRI device, which is a very high value device, or a very sensitive device which measures the, say, earthquake. So those are important device which can be affected by presence of external electric field. To avoid that, we place them inside a metal casing so that they don't get distracted, they don't give us wrong values. So they inside, basically they have a completely metallic cage so that external electric field does not change anything on that device. Okay, this is also called electrostatic shielding. Now, what are dielectrics? Dielectrics is very important in this chapter. We are starting with a new concept called dielectrics. Dielectrics are non-conducting substances. In contrast to conductors, they have no or negligible number of charge carriers. So dielectrics are basically insulators. They are insulators. For example, a paper. okay, or mica sheet. Mica sheet is same that used in makeups there, so that the skin glows. You may have seen in different actresses or famous personalities, they use something on their skin so that it glows. Basically those are mica, and mica is a mineral which is appear to be in the form of sheet. So if you are using a mica sheet, that is also a dielectric. Common example, paper is also a dielectric medium. Okay. It turns out that the external field induces a dipole moment by stretching or reorienting the molecules of the dielectric. Even though they do not have any free electrons, they do not conduct electricity, they play a major role in static electricity, where you can induce an electric field inside the dielectric. Okay. The collective effect of all the molecular dipole moments is the net charges on the surface of the dielectric, which produces a field that opposes the external field. The opposing field is so induced, it does not cancel the external electric field, it only reduces the effect. The extent of the effect depends on the nature of the dielectric. So for example, here we have, in case of metals, what is happening, the electric field is completely cancelled by the internal field. In case of dipole, the external electric field is this, the internal electric field is opposite, but it is not cancelling each other. So initially for a conductor, E naught E outside into E inside equals to 0, but in case of dielectric, E outside plus E inside is not 0. Okay. Now there are two types of dielectric, non-polar and polar. Okay. This is also very important for your PUC. Based on this, we have seen questions almost every year. 3 times it came in last 5 years. So this is a very important concept. Difference between polar and non-polar. The MCQ questions based on polar and non-polar, both are important. A non-polar molecule, the centers of positive and negative charges coincide. So normally this is called non-polar. So where if you see that positive, center of positive and negative are coinciding, that means we have an atom, right? Atom has a positive charge at the center, and we have electrons orbiting around it. Now if the orbit is symmetrical, or the number of electrons are symmetrical, even, okay, so if there are 2 electrons, say 1 electron here, another electron over here, so what happens is that the center of positive and negative, everyone is actually falling at the center, so they have the same centers. Okay, so if positive and negative are falling at the same point, okay, average distance, okay, if you calculate the average of these two charges, you will get at the center. Okay, so this is called when centers of positive and negative are coinciding with each other. So they do not have any electric field of their own, and they do not possess any dipole moment. A net dipole moment is 0. Okay, so they do not form a dipole normally. But when you apply external electric field, they are negative and positive. Obviously negative will be repelled by the electric field, positive will be attracted by the electric field, and you will get a dipole moment developed inside the molecule. Okay, it can be a molecule, it can be an atom as well. So because this electric field is developed, they are called non-polar normally, but in presence of electric field, they do get an induced polarization. Okay, the molecule then has a no permanent or intrinsic dipole moment. Example of non-polar dipole molecules are oxygen and hydrogen molecules, which because of symmetry have no dipole moment. Okay, oxygen and hydrogen, they do not have any dipole moment. They are examples of non-polar dielectrics. Now polar dipole, polar molecules, it is also very, very important. Polar dipole dielectrics. A polar molecule is one which in which the centers of positive and negatives are separated even when there is no external field. So if this is an example of polar molecules, if you see that positive and negative, they do not coincide. Example is HCl. Okay, so the electron pair which they are sharing, it does not stay in the middle. If it is stayed in the middle, center of positive and negative should have coincided, but because of higher electron affinity of chlorine, the electron pair is shifted towards chlorine, and chlorine becomes delta minus and hydrogen becomes delta plus, and there is a net dipole moment developed from negative to positive. So this is an example of polar molecule. Water is also a polar molecule. That's why water is a good solvent. If you have remember in chemistry, water is a good solvent because water is a polar molecule. Such molecule have a permanent dipole moment. Molecular level, they have a permanent dipole moment. But if you consider a bulk material, okay, in polar crystal, the net dipole moment is still 0. In a polar crystal or polar bulk material, if you consider a bulk material of polar molecules, for example, if you take water as in a beaker, okay, or water as an ice, the net dipole moment is still 0 because the dipoles are randomly oriented, and in case of random orientation, when you take the average, you get 0 dipole moment. But if you take only one single molecule of water, they have a permanent dipole moment. Remember this, the net dipole moment for a crystal of polar molecule is still 0. Okay, this is because the molecular dipoles are randomly arranged. In case of random arrangement, the average is always 0. Okay, polarization, very important. Polarization, when a polar or non-polar dielectric, this is applicable to both polar as well as non-polar. Okay, a dielectric develops a net dipole moment in the presence of external electric field. Okay, when you apply external electric field, a net dipole moment is developed. The dipole moment per unit volume is called polarization and is denoted by capital P. Okay, it's a vector quantity. It's a vector quantity. For linear isotropic dielectric, this is applicable only for linear isotropic dielectric. Okay, I hope you are familiar with these terms. You have linear means all the dipoles are linearly arranged, and isotropic means it is symmetrical across. So this is for linear and isotropic dielectric, P vector is equals to epsilon naught into chi E into E. Chi E is called the electric susceptibility. Chi E is called electric susceptibility. We have studied magnetic susceptibility. Chi E is called electric susceptibility. It's a dimensionless quantity. It does not have any dimension. Okay. Which of the statement is false in case of polar molecules? So 2021 in KCET this question came. Centers of positive and negative charges are separated in the absence of external electric field. Centers of positive, so we have to find the false statement. Okay, false statement. That means 3 is correct, 1 is wrong. Centers of positive and negative charges are separated in the presence of external electric field, do not possess permanent dipole moments. Ionic molecule HCl is an example of polar molecule. Okay, which of the statement is false in case of polar molecules? This is a molecule based question. Option C, do not possesses permanent dipole moment. Yes, this is correct answer. Remember that centers of positive and negative are already separated in the absence of electric field, and in the presence of electric field also it is still separated. So option A and B both are same. Do not possess permanent dipole moment is incorrect because they do possess permanent dipole moment in molecular level. It is a bulk crystal, it is still correct. But for molecular level, do not possess permanent dipole moment is wrong. Okay. Next question. It is from 2024. under electrostatic condition of charged conductor, which among the following statement is true? So 3 of the statement is false, 1 is correct. The electric field on the surface of a charged conductor is sigma by epsilon naught, where sigma is the surface charge density. The electric potential inside a charged conductor is always 0. Any excess charge resides on the surface of the conductor. Net electric field is tangential to the surface of the conductor. This will be sigma by 2 epsilon naught. Yes, all questions we are discussing are important only. All questions we are discussing are important only. So any excess charge resides on the surface of the conductor is the correct answer. Any excess charge resides on the surface of the conductor is the correct answer. Now, this question, answer these 2 questions. I think most of you have answered. Let me check now. 11D and 12D, both of them you have answered, and Pradyum is saying 11C, 12A. Let's see. For linear dielectrics, the ratio of dielectric polarization to the magnitude of the applied electric field is equal to mobility, epsilon naught into susceptibility, dipole moment, permittivity. So remember that P is equals to epsilon naught chi E electric field. So the ratio of dipole moment per unit volume divided by electric field is epsilon naught chi E, that is option C. Susceptibility, epsilon naught into electric susceptibility. So option C, Pradyum was correct. The dimension of electric polarization. The dimension of electric polarization. Now very tricky question. Polarization, do not use this formula to find the dimension of electric polarization. Electric polarization is basically polarization per unit volume. Okay, so electric polarization is dipole moment per unit volume. So what is dipole moment? Dipole moment is Q into 2A divided by volume. And if you remember, we have done the calculation of this dipole dimension of dipole, which is given by dimension is lat. Okay, lat was the dimension of dipole. Q is A into T, and there is a 2A is L, so lat, and volume is given by L cube. So it becomes L to the power of minus 2 A into T. Okay, L to the power of minus 2 A into T. So option A is correct. Yes, Pradyum was correct in both cases. Gladwin was not correct in both cases. Okay, Bagu Katwar is saying option A. No, option A is option B is not correct. Okay, it is epsilon naught into chi, that is, this is epsilon naught times susceptibility, electric susceptibility. This is called electric susceptibility. So epsilon naught into electric susceptibility is correct answer for this question, because dipole moment can be polarization can be expressed in terms of electric field like this. And what is polarization? Polarization is dipole moment per unit volume. Polarization is dipole moment per unit volume. Polarization is capital P, dipole moment is small p. So don't make mistake between these two p's. Even though both are p, one is smaller, one is bigger. This is the net dipole moment per unit volume. Dipole moment is lat, volume is L cube, but this is in division. So from here we get L to the power of minus 2 into A into T. Okay. I was confused for option D. Which one? Which question? This one, permittivity. Permittivity is epsilon naught. Permittivity is epsilon naught. Permittivity of free space is epsilon naught. Permittivity of any other medium is epsilon. But epsilon generally comes in terms of dielectric, okay, where you multiply epsilon naught with the dielectric constant, you get permittivity. This one is obviously not correct because mass is not there in case of polarization. Okay, polarization, mass is obviously not involved. So either this one or this one. Now if you have understood that concept, that because we are talking about polarization where mass is not involved, okay, you can eliminate the answer saying, okay, this is not definitely not correct, this is definitely not correct because mass should not be there in the polarization. LAT is the dimension of dipole moment. LAT is the dipole moment, so definitely other than that must be L to the power of minus 2 A into T. Okay, clear? Now move on. Now this is also the most important concept in terms of KCET as well as PUC, capacitor and capacitances. Okay, capacitor, all concepts of capacitor and capacitance are important not only for your PUC but it is also important for your board, your KCET exam as well. Capacitor is a device that is used to store charges. Very simple thing. So it is a device which can store charges and discharge it whenever required. That's how it is work. That is the main function of it. A capacitor is a system of two conductors separated by an insulator. This insulator can be, this can be air or this can be a dielectric as well. Okay, for all practical purposes definitely dielectric, for our class, for our level mostly air. In practical applications whenever you see a capacitor they are always having dielectric, but in our class whenever we study we will use air only. When I was a student in my college we even used water capacitor as a ice capacitor. In higher level, post graduation level, but obviously that is not there in your case. So in only we have air capacitor. Dielectric capacitor can come in a very small number of cases in KCET. PUC level air capacitor is the boss. Usually in practice two conductors have charges capital Q and minus Q with potential difference V equals to V1 minus V2 between them. Q is called the charge of the capacitor, though in this case in fact the charge of one of the conductors, the total charge of a capacitor is 0. So when you say this is a capacitor, capacitor generally represented by two equal lines, okay, and this is the symbol of the capacitor. So this side has Q, this one has minus Q. There is an electric field developed inside the capacitor plates. This one say has a potential V1, this one say has a potential V2. So V1 minus V2 is the net potential. Also when we say charge of a capacitor we mention plus Q. Plus Q or Q is the charge of the capacitor or charge stored in the capacitor, even though the net charge of the capacitor plates is 0. Net charge, total charge, if you can combine these two sides, total charge would be still 0. But why do we do not say that the net charge is 0? Because if you conduct them through a resistor, okay, this one has higher potential, this one has lower potential, so there will be a current flowing in this capacitor. Basically energy is being stored and that is being stored in the form of charge. That's why we do not say that charge is 0. Only in case if you see a question where it is mentioned the total charge of the capacitor. This is very, very common tricky question, MCQ question that might be asked in your PUC level, where the total charge of the capacitor is Q, Q by 2, 2Q, 0. Remember, total charge of the capacitor is 0, even though we say that charge stored in the capacitor is capital Q. Okay, here are some examples of capacitor diagrams. Those who have seen any electrical circuit, these are very common portions. When we were kids we used to have CRT TVs. CRT TVs means the long back one TVs, not the flat panel TVs. okay, and inside those panels, and it get damaged very soon. There are multiple problems happen, and whenever the electrician guy came, he used to open the back side of the TV, and inside that back side we used to see a lot of these capacitors connected in the circuit. Okay, nowadays it is no longer there. We use more reliable flat panel LEDs or LCDs. They also have capacitors, but we generally do not, that generally do not get any problems, so we do not need to repair it very often. So maybe you have seen, maybe you have not seen. If you have seen, very good, you can mention that in the chat. Edu Murai is saying, sir, second preparatory start on 9th Monday, so please electronics and hardware subject, Madhuri, please, please. So electronics and hardware is not, we do not have this subject in our Deeksha colleges. I am extremely sorry, we may not be able to cover that in our channel. We will try, but electronics is okay. Electronics is one topic. Electronics and hardware, that subject is not there. Okay. Yes, physics is there in every cases. Please tell about second pre-board timetable. Second pre-board is starting on 19th. If you want me to discuss the timetable, I will discuss once this lecture is over. I can discuss in detail. I can open the timetable in here and I can discuss it. 19th it is starting. If I remember, it is starting with Kannada. Then I think English is there. First science subject is physics. Then we have chemistry, then mathematics, and last is biology. Okay. It will not be a very long timetable. Is not as long as in the first preparatory. It is the duration is slightly shorter than the previous exams. Okay. 22nd is physics, if I remember. Okay. 21st there will be a live in Deeksha Karnataka, where I will come and take live for your pre-board preparation. So don't worry, if you are wondering about pre-board, second pre-board preparation, I will help you in that as well. That will be a comprehensive all chapter long marathon. Okay. Q is called the charge of the capacitor, though in fact the total charge is 0. The charge of the capacitor leaks away due to the reduction of insulating power of the intervening medium. So if you leave a capacitor charged, okay, if you leave a capacitor charge and you come back after say 10-15 days, you will see that the capacitor does not have any more charges, almost zero charges, negligible charges. What happens is that the charges, because there are positive charges, there are negative charges on these plates, the charges do get leaked from this side to this side because negative electrons can move. So electrons slowly start moving in the presence of electric field. Electric field is very high electric field present from this side to this side, and electrons move in the opposite side of the electric field, and after time, over time, the electrons start leaking from negative side to positive side, and total charge becomes 0 in very quickly. Okay, so total charge of the capacitor goes to 0 if you do not take precautions. There are some ways to take precaution, but generally we use capacitor in live circuit only. For example, capacitor is used in fans. Fan is a very common place where a capacitor is used. Okay, and it works on the live, whenever current is flowing through it, it works. Okay, it is not like your power bank. Power bank is something where you can store the energy for longer time. Okay, capacitor is not power bank. Okay, battery's principle is completely different than capacitor, even though both can be considered that they are storing charges. Battery does not directly store charge, it stores energy. Capacitor is basically storing charges. Okay, and you cannot use a capacitor as a battery because it will discharge very, very fast. Okay, but component of your charger is a capacitor. If you open your charger, if you have an old charger, if you are able to open it, do not try it at home, by the way. If you can open the charger, you might see a capacitor like this present inside the charger. Okay, maybe you will be able to identify them, maybe you will not be able to identify it because there are different shapes and sizes of the capacitor. Okay, anyway. Yes, Pradyum, as I mentioned, there will be live. Ban is saying we have physics on 21st. I think the schedule is common, no, for all across the state. because it is published, the schedule is published by the PU board itself. It is not like published by individual colleges or individual districts. It is common across Karnataka. So you can check 3-1 काफ़ी है. Okay, because as I know, the schedule is common for all the colleges, unless your college is taking your individual pre-board, then it might be a different date. Otherwise, all Karnataka state, those who are giving the exam on district level papers, okay, it is on 22nd of Jan. The potential difference V is proportional to, now capacitor, in case of a capacitor, the potential difference which is developed between the plates. So if you consider the plates, okay, as I mentioned, one plate has capital Q, another plate has minus Q, okay, there is a potential difference developed between the plates. Okay, there is a potential difference developed between the plates. This potential difference between the plate is directly proportional to the charge Q, obviously. Okay, more charge, higher charge means higher potential. So potential is directly proportional to Q. Okay, and if you want to remove this potential's proportionality sign, you have to induce a constant. Okay, you have to induce a constant, and that constant is called, this proportionality constant is called capacitance. Actually, it is coming as 1 by C. So we can say Q equals to C into V, or the ratio of Q upon V is capacitance, which is constant. Okay, so remember that if you change voltage, okay, if you change voltage, the charge stored in the capacitor will change, but the capacitance itself will not change. Okay, there are some trick questions that had came in the past in KCET as well as in your board exam, where they will say that the charge is doubled, the potential is doubled. What will happen to the capacitance? Capacitance will not change on Q or on V. Okay, even though C equals to Q by V, if you change Q, what happened will that V will increase. If you increase V, Q will increase. If you increase Q, V will increase, but their ratio will remain constant. C does not depend on Q or V. Okay, so C equals to Q by V. The constant C is called capacitance of the capacitor. C is independent of Q or V. Even though C is equals to Q by V, okay, for a given capacitor, C is independent of Q on and V. So on which capacitance is dependent? We'll come back. The SI unit of capacitance is farad. Okay, farad is coulomb per volt. Okay, farad is coulomb per volt. Try and find the dimension of the capacitance that might come in your exam. So just remember that this is very easy unit. Volt is joules per coulomb and capacitance is coulomb per volt. So it is basically coulomb square by joule. Coulomb square is this is capacitance, by the way, dimension of capacitance, and C is charge. Charge means A into T whole square, and here it will be M L square T to the power of minus 2. So if you compare it, it will be M to the power of minus 1, L to the power of minus 2, okay, T to the power of 4, A square. Okay, this is the dimension of capacitance. Very tricky but not difficult. Okay, you can remember it. Those who are appearing for JEE mains, can be a potential question. In practice, farad is a very big unit. The most common unit used in practice are microfarad, nanofarad, picofarad, etc. Okay, microfarad is 10 to the power of minus 6 farad, nanofarad obviously minus 9, and pico is minus 12. From the above equation, we can see that large C is small for given Q. Okay, if you have a large C, okay, V is small for large C, V is small for given Q. This means a capacitor with a large capacitance can hold, okay, capacitance with a large capacitor can hold very large amount of charge without increasing the voltage. Voltage can keep, we can keep the voltage very small, but still we can store a large amount of charge. This is of practical importance. So basically what do you want? We want to spend little amount of money, but we want to get a lot of things, right? So you can consider that voltage is like money, charge is like the things that we want to get. Okay, so you spend say 100 rupees and you want to buy a lot of chocolates, you want to buy some coins for your games, you want to buy some books for your study or maybe for reading comics. So you want to buy a lot of things using 100 rupees, but 100 rupees can only buy some small amount, right? But if you can get to a market where everything is cheap, so that you get everything almost for free. So large capacitance is like a free market, okay, where you can store a large amount of charge, but voltage will increase by a small amount. Okay, now parallel plate capacitor. Parallel plate capacitor is the most common capacitor used in our day-to-day life. Even if you see a capacitor like this, okay, this is also a parallel plate capacitor. This looks like a cylinder, but it is a parallel plate capacitor. Now, if you're wondering why I have drawn these two lines like this, those who studied electronics, they might know that large arm is actually positive, small arm is negative. Okay, so capacitor has a positive and negative. And how it is these cylindrical capacitors are parallel plate capacitor, because inside it we have two very long sheet of conducting surfaces separated by a thin sheet of mica or paper. Okay, so basically it's a very long sheet of conductor, okay, and inside we have a thin paper, and then it is rolled. Okay, and because it's rolled, we get this shape. Okay, they are rolled such a way that positive and negative plates are not touching each other. So very simple design, but very effective. Actually, if you increase the area of a capacitor, we can increase the capacitance. We'll see that. A parallel plate capacitor consists of two large plain parallel conducting plates separated by a small distance. The space between the plates can be filled with dielectrics to increase its capacitance. Okay. Now, capacitance of a capacitor normally is given by Q by V, which is A epsilon naught by D. So capacitance does not depend on Q, does not depend on V, but it depends on the area of the plate and the medium, the epsilon naught, and divided by the distance between the plates. So if you keep the distance small, if you keep the area large, capacitance will be very, very large. Here we are only considering air capacitor. Air capacitor means there is no dielectric medium present between the plates. Okay, so it is simply A epsilon naught by D. This is a very common question. Write the two factor on which the capacitance of a parallel plate capacitor depends. So basically capacitance is directly proportional to area, inversely proportional to the distance between the plates. Very common question in your PUC exam. Chirag, what is your question, Chirag? I miss your question. Chirag is saying, please reply. We have physics on 22nd. Chirag, I don't get your comment. Can you please post it again? And as I mentioned, Mayuri, I will tell you the timetable after this lecture is over. I have to go to the website and show it to you, which is the Bangalore. You can search for it, Bangalore North Principals association. There is a Bangalore North. All the principals of government colleges, they have an association. There it is published. You can go and check that out. In the circular section, it is there. And it is same for Bangalore North, Bangalore South, across Karnataka, the dates are same. And because it is published by the PUC board. So capacitance depends only on the geometry of the system. Geometry means area and the distance between the plates. That's the meaning of geometry. Okay. Next, effect of dielectric in the capacitor. Okay, Chirag, if you are listening to me, you can mention what is your question, because I don't see any question posted by you. Okay, Chirag. Now, so here we had previously we had a dielectric capacitor, and in between the plates we had only air. Okay, between the plates we had only air, and we calculated the capacitance to be A epsilon naught by D. Okay, now what will happen if we put a dielectric slab between the capacitor plates? If we put a dielectric slab between the capacitor plates, whether it will increase or decrease, what will happen? Okay, let's find out. So let us insert a medium of dielectric constant K between the plates, and we are filling it completely. Even though you are seeing some gap left, there is no gap left. It is completely filled inside in the capacitor. In that case, the capacitance is no longer initial capacitance was A epsilon naught by D. Now the capacitance will be A epsilon by D. What is epsilon? Epsilon is the permittivity of this medium. Epsilon is the permittivity of the medium. Now what is permittivity? Permittivity of a medium is given by dielectric constant times the free space permittivity. So epsilon equals to capital K into epsilon naught. It is capital K. Small k refers to Coulomb constant, capital K refers to dielectric constant. Okay, so we can say that. So let me see, this is C dash. So we can write this as A into K, AK epsilon naught by D. Okay, so we get A K epsilon naught by D. So basically what we got the original capacitance on the previous case. The original capacitance in the previous case was A epsilon naught by D, and now we got the capacitance here as K times C. So if you increase the capacitance, increase the dielectric medium, inside a dielectric medium, the capacitance increases. So to increase the capacitance, we have to insert a dielectric medium between the plates. Very important. So how can you increase the capacitance of a capacitor? Increase the area, decrease the distance, but both have some physical limits. You cannot increase the area by very high amount. You cannot decrease the distance beyond certain limit. Okay, if you decrease the distance too much, then charges will leak instantly. So other way to increase the capacitance is by inserting a suitable dielectric medium. Okay, suitable dielectric medium. For example, the parallel plate capacitor I showed you, they generally used a waxed paper. Okay, so paper dipped in wax, simple paper dipped in wax, so that both side of the paper is covered with wax. Okay, and now that is used as dielectric medium between the practical cases. In practical cases, that is the most commonly used dielectric medium. So it has paper, it has wax, and that's how you can create a insulating layer between the plates, which is much better than air. Okay, now combination of capacitors, obviously there are two combinations. Series combination. Series combination is when you connect the capacitors one by one. Now I am not doing the derivation. If you want me to do the derivation, mention in the chat immediately, so that this is C1, C2, C3. Now if you want to replace it with using a common equivalent circuit, then 1 by C equivalent is given by 1 by C1 plus 1 by C2 plus 1 by C3. Okay, so this is the series combination. Series combination of capacitor is same as parallel combination of resistors. So don't be confused between series combination of resistors and series combination of capacitors. Okay, in case of two capacitors, the formula can be directly written as C equivalent equals to C1 C2 by C1 plus C2. Okay. Manjunath is saying, sir, will you teach portion of first year? Yes, Manjunath, yes, we will teach portions for first year in CET. That will be done in our exclusive KCET series, Master Stroke. We will start Master Stroke very soon. There we will discuss only KCET level question. Here we are discussing KCET and PUC combined. That's why obviously for your PUC, first PU is not important. So that's why we are not doing first PU content right now. But yes, we will cover first PU content as well. Don't worry. Parallel combination of capacitor is this, where one capacitor is connected after that. And anyway, don't think too much about first PU, because first PU weightage is not very high. If you are a dropper also, don't worry too much. First PU weightage is not very high. You should mainly focus on second PU. Second PU is more important. If you finish all the chapters of second PU, first finish all the important chapters of second PU, then finish the other chapters of second PU, then 40 marks is guaranteed. Okay, once 40 marks is guaranteed, then move towards first PU. Do not waste or think too much first PU. You don't have to think about it. Okay, first PU questions, if you follow our lectures, you will be able to answer at least 14-15 questions from first PU. Okay, because some questions of first PU may be tricky, and if you want to waste too much time on that, you might lose out on the 40 marks that is coming from your second PU, right? Now, and what is the formula for parallel combination? Formula for parallel combination is very easy. C equivalent is given by C1 plus C2 plus C3, right? Now, energy stored in a capacitor, very important and interesting portion. Energy stored in a capacitor is normally can be written in three forms. One is half CV square, half QV, or half Q square by C. Okay, so this is called energy stored in a capacitor. These all formulas can be handy based on questions. Okay, now energy density. Energy density is what is energy density? Energy density is energy stored per unit volume. Energy stored per unit volume is called energy density of the capacitor, and that is actually half epsilon naught E square. This derivation is not part of the syllabus. Okay, only the formula is there. So U is half epsilon naught E square is the energy density of the capacitor, and as you can see, the energy is stored in the form of electric field. Energy is stored in the form of electric field. Okay, so electric field is developed between the plates. So suppose this is positive plate, this is negative plate. Electric field is developed, and that electric field is actually storing the energy. How it is stored? Is it stored via charges? No, it is not stored via charges. It is stored only in the electric field that is being there between the plates. Okay, so between the plates, if you increase the voltage, okay, if you increase the voltage, potential electric field is also increased, and that's why the energy is being stored inside the capacitor. Now we will solve questions only. From now on, only questions. First we will solve some KCET level, some board level, then we will solve very important numerical questions as well. Okay, so if you are staying till now, try to hold on for a little bit more. Within 30 minutes we will be over. So try to put your concentration right now. A parallel plate capacitor of capacitance C1 with a dielectric slab between the plates is connected to a battery. It has a potential difference V1 across its plate. When the dielectric is removed, the potential difference are C2 and V2 respectively. Then, so we have a parallel plate capacitor, okay, capacitance C1 with a dielectric slab between the plates. So its capacitance is C1 and it has a dielectric plate between the plates. Now what you have done? Okay, the voltage between the plate, voltage across them is V1. Okay. When the dielectric is removed, the potential difference are C2 and V2. So now it is connected to an external battery. Remember, it is mentioned that it is connected to a battery, and when it is connected to a battery, the capacitance is C1, potential is V1. Now you remove the dielectric medium. You remove the dielectric medium, what will happen to the capacitance and the voltage? What will happen to the capacitance and the voltage? So now it is C2, V2. Okay, what is the relationship with C1, C2 and V1, V2? Answer quickly. Answer quickly, answer. Okay, I think you are confused. So parallel plate capacitor with capacitance C1, a dielectric slab between them. So initially the capacitance must be higher. Okay, so because if you remove the dielectric, the capacitance decreases, so initial capacitance must be higher. So C1 must be greater than C2. C1 must be greater than C2. Okay, here also in the question slightly one small error is there. Okay, C1 must be greater than C2. Now what about V1 and V2? So in both cases they are connected across the battery. So when it is connected across the battery, it has no choice but to have the same voltage. It has no choice but to have the same voltage as the battery. So V1 will also be the same voltage as battery, V2 will also be the same voltage as the battery. So V1 must be equals to V2. If it was something different, when you are removing it from the voltage source and then removing the slab, that can give you a different answer. Okay, so for that you have to use Q is equal to CV, C1 V1, then Q is equal to C2 V2. Charge stored in the capacitor would have remained same, but that is a JE level question, generally do not come in KCET. But you should remember that in case it is cut from the battery and then you remove the dielectric slab, so then it will depend on in the formula Q equals to C1 V1. As C1 is decreasing, V2 has to increase. But here, because it is still connected to the battery, as nowhere it is mentioned battery is removed, so that means it is still connected to the battery, so voltage should remain constant, capacitance should decrease, so C1 is greater than C2 and V1 is equals to V2. Clear? Question number 14. A parallel plate capacitor is charged by connecting a 2-volt battery across it. Okay, let's see. A parallel plate capacitor is charged by connecting a 2-volt battery across it. It is then disconnected from the battery and a glass slab is introduced between the plates. Which of the following quantities is decreased? So this is the question where I was saying that battery is connected and then it is disconnected. So initially it was no mathematics is there. Obviously KCET level this question generally will not come as a with the mathematics calculation might come in JEE mains. Okay, so here we have a capacitor plates and we had a initially it is only air. Initially it is only air. Now it is connected to a 2-volt battery. Okay, so what will happen? You charged it to 2 volt. So basically when you connect it to a 2 volt battery, the capacitor is charged fully to 2 volt potential. Now you remove the capacitor from the battery. So now it is disconnected. So capacitor has a 2 volt potential. Okay. Which of the and a glass slab is introduced. Now you have introduced a glass slab between the plates. What you have done? You have introduced a glass slab between the plates. Okay. Pradyum is saying 14D. Let's see. So you have introduced a glass slab between the plates. So once you have introduced the glass slab, what happens is that the capacitance increases. The new capacitance C dash is more than that of original capacitance. Okay. So the voltage, the new voltage must be less than that of the old voltage. So if capacitance increases, voltage decreases. Okay. If capacitance increases, voltage decreases. That is the point we have studied, right? Now what else? The energy stored will not be same. Energy stored is half Q square by V. So if you remember, half Q into V. Okay, so half Q into V. So initially the charge in both cases is same. Both cases will have same charge. Charge is conserved. Voltage and capacitance are not conserved. Energy is also energy, even though we say energy is conserved, but not always. Energy can be lost. Okay, but charge, if it is in an isolated system, charge is conserved. Okay, so charge is conserved over here. So because charge is conserved, what happens? Half Q into V is the energy stored. As voltage is decreasing, energy should decrease. So energy, final energy is less than that of initial energy. So energy is decreasing. Energy is decreasing, but charge remains same. So energy stored and so which quantities decrease? So energy stored decrease. Energy stored decrease. Potential energy also. Potential also decreases. So potential difference and energy decreases. Option D is correct. Charge and potential difference, charge remains same. Capacitance and charge, again charge remains same. So these are all wrong. Capacitance increases. So option D, potential difference and energy stored both decreases. Now next two questions. The capacitance of a capacitor is 6 into 10 to the power of minus 6 farad. It is connected to a 200 volt cell. The energy released on discharging it fully. So this question came in I think 2024 PUC. 2024 PUC, this question was there. Answer quickly. And question number 16, if charge in a capacitor is doubled, then the capacitance is. Common question. Who want to answer? The capacitance of a capacitor is 6 into 10 to the power of minus 6 farad. It is connected to a 200 volt cell. The energy released on discharging it fully. So the energy released in discharging it fully, obviously half CV square, the energy that is stored when it was fully charged. Simple. So C is given as 6 into 10 to the power of minus 6 and voltage is 200 volt. So just simple mathematics 3. So 3 into 10 to the power of minus 6 into 4 into 10 to the power of plus 4. Okay, 200 can be written as 2 into 10 to the power of 2. Whole squaring that, you will get 4 into 10 to the power of 4. So you get 12 into 10 to the power of minus 2, that is 0.12 joules. 0.12 joules, correct answer option A. Next question, if a charge in a capacitor is doubled, then its capacitance. So we know that capacitance is equals to Q upon V, but if you increase the charge, voltage will also increase, capacitance will remain same. Capacitance does not depend on charge or voltage, it only depends on the geometry of the capacitor, so here it will be remain same. So charge doubled, capacitance will remain same. Next, now we will be solving some very important numerical question from this chapter. All the numericals are super important. Okay, calculate the potential at point P due to a charge of 400 nanocoulomb located 9 centimeter away. Okay, obtain work done in moving a charge of 2 nanocoulomb from infinity to the point P. Does the answer depend on the path along which the charge is moved? So first we have to calculate the potential. What is the charge? Charge is 400 nanocoulomb. And we are trying to find potential at this point P. So what is the distance? Distance is 9 centimeter. Okay, so how to find the potential? What is the formula for potential due to a point charge? KQ upon R. So what is K? K is 9 into 10 to the power of 9. Q is 400 nanocoulomb and distance is 9 centimeter. Okay, so 9 cancels, 10 to the power of 9, 10 to the power of minus 9 cancels, we get 400 into 10 to the power of plus 2, that is 4 into 10 to the power of 4. Okay, so this is the potential at this point P. Okay, now what is the work done to move a moving a test charge of 2 nanocoulomb from infinity to point P. So the work done is given by basically Q into potential. That is the energy of the charge. Very simple. So if you can calculate the energy that is stored in the charge, you can calculate the work done. How to calculate work done? So Q is given by 2 nanocoulomb, 2 into 10 to the power of minus 9. Potential is given by 4 into 10 to the power of 4 volt. Now what is the energy unit of work done? Don't miss the unit. Don't miss the unit. Work done is joules. Okay, so work done is joules. So it will be 8 into 10 to the power of minus 5 joules. Very simple, very easy. Generally potential based problems are slightly easy because you don't have to use vector symbols and signs, so that's why generally they prefer electric charges as numerical questions, but many a times questions from this chapter also has came. But remember that if you are getting a numerical from this chapter, then you are lucky because not too many vector related complicated calculations are there. Now one more important part is that is it dependent on the path through which it is moved, because you are moving from infinity. Okay, you are moving the charge from infinity, whether this path or which path. So as we know that work done is independent of the path. Work done depends only on the starting point and the ending point. It is not dependent on the path, so it is independent of the path taken. Independent of the path taken. This is also, if you don't write it, you will lose 1 mark. Remember, so you have to read the question. Yes, correct. So when you are answering the question, remember you also have to answer each and every part of the question. So does it answer depend on the path along which the charge is taken? If you miss out on this answer, 1 mark will be deducted. So for a very simple trivial reason, if you miss, your marks will be deducted. So don't do that. Next, in a parallel plate capacitor with air between the plates, each plate has an area of 4 centimeter square. It is centimeter square, okay, not 2, and the distance between the plate is 2 millimeter. Calculate the capacitance of the capacitor if this capacitor is connected to a 100 volt supply. What is the charge on each plate of the capacitor? Okay. So first of all we have to calculate the capacitance. Capacitance is given by epsilon naught A upon D. Epsilon naught A upon D. What is epsilon naught? Epsilon naught is 8.854 into 10 to the power of minus 12. Generally they will provide this value. It was given in this question, but it was taking too much space, so that's why I have deleted that option. Okay, 8.854 into 10 to the power of minus 12. Area of the plate is 4 centimeter square. So remember, centimeter square means 10 to the power of minus 4. Okay, so centimeter, 1 centimeter is 10 to the power of minus 2 meter. 1 centimeter square is basically 10 to the power of minus 2 meter whole square, that is 10 to the power of minus 4 meter square. So to convert centimeter square to meter square, you have to multiply 10 to the power of minus 4. So don't make that mistake. Now, what is distance? Distance is given 2 millimeter. 2 millimeter means 2 into 10 to the power of minus 3. Okay, so this cancels, you get 2. Okay, and you get this is approximately 17.6, 17.6 17.7, 70, approximately 17.7 into 10 to the power of minus 9 minus 13 farad. So approximately 1.77 picofarad. So capacitance is 1.77 picofarad. Okay. Now what? Capacitance we have calculated. If this capacitor is connected to a 100 volt supply, what is the charge on each plate of the capacitor? So now this capacitor is connected to a 100 volt supply. You just need to calculate the charge. So what formula? Q equals to CV. Very simple. Q equals to CV. C is 17.7 into 10 to the power of minus 13 into voltage is 100 volt. So it will be 17.7 into 10 to the power of minus 11. Okay, or 0.177 nanocoulomb. 0.177 nanocoulomb. Yes, correct. Okay, check the calculation once if I have made any mistakes. I don't think so, but anyway, now, so this kind of questions are common. We will solve, this is not all, we will solve more questions. 3-point charges, 3 nanocoulomb, minus 2 nanocoulomb and 4 nanocoulomb are placed at the vertices of ABC of an equilateral triangle ABC of sides 0.2 meter. Calculate the potential energy of the system. Also calculate the amount of work required to place the same charges at the vertices of equilateral triangle of side 0.1 meter. So first we have an equilateral triangle of sides 0.2 meter. So meter is given here, so that is one thing, and it is an equilateral triangle. 3 nanocoulomb, minus 2 nanocoulomb and 4 nanocoulomb. You have to calculate the potential energy of this system. So this is say U1. This is configuration 1. How to do that? Simple, 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R31. So basically you have to take two pairs and divide them by the distance. Now here distances are same, R12, R23 and R31, all the distances are same. So we can take that as common, and 1 by 4 pi epsilon naught is 9 into 10 to the power of 9 divided by R. all distances are equals to r, and we have to multiply with the pairs. So 3 into minus 2, 3 into minus 2, all of them are nanocoulomb, so we will get a nanocoulomb square at the end, so we will take care of that in a while. Next is minus 2 into 4 plus 4 into 3. Okay, so 9 into 10 to the power of 9 divided by 0.2, and here we got minus 6 minus 8 plus 12 and into 10 to the power of minus 18. Why minus 18? Nanocoulomb, 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 nanocoulomb. So 2 nanocoulomb, all of them are nanocoulombs. So 10 to the power of minus 18 should be here. Now what? Now we have to calculate the potential energy. So U1 is equals to 45 into 45. How do we get 45? 9 divided by 0.2 is 45, and here we have minus 14 plus 12, that is minus 2, right? Minus 6 minus 8 minus 14 plus 12 minus 2 into 10 to the power of minus 9. So here we had plus 9 minus 18, so minus 9. So you get 90 into 10 to the power minus 90 into 10 to the power of minus 9, or minus 90 nanojoules. Okay, the energy of the system is minus 90 nanojoules. Also calculate the amount of work required to place the same charges at a vertices of equilateral triangle of side 0.1 meter. Now you are changing it to a vertex of 0.1 meter. How much work is to be done? Initially they are at all 0.2 meters. Now you are decreasing the distances to 0.1 meter. Don't calculate everything from the scratch. You have to find the final potential energy. This is U1. Final potential energy U2, you can start directly from this equation. Okay, you need to start. I think my screen is frozen. Just give me a second. So you just need to start from this equation, and what you have to do, you need to put, instead of this 0.2, you have to put 0.1. That's it. Don't start from the scratch. 9 into 10 to the power of 9 divided by 0.1. This calculation is common for everyone. Okay, so minus 2 into 10 to the power of minus 18. Okay, so you get this as 90 into minus 2 into 10 to the power of minus 9, that is minus 180 nanojoules. Minus 180 nanojoules. Okay, so what is the work done? Work done is given by final potential minus initial potential. Okay, so final potential is minus 180, initial potential was minus 90, so the work done will be minus 90 nanojoules. Okay, so work done will be minus 90 nanojoules. Okay, yes, the last question. Give me a second, guys. Now, last numerical question, then we will solve a few more practice questions, and obviously the formula sheet will also be provided. 3 capacitors of capacitances 2 microfarad, 3 microfarad, 6 microfarad are connected in series. Determine the effective capacitance of the combination find the potential difference across 6 microfarad capacitor if the combination is connected to a 60 volt supply. So here we have a 2 microfarad, a 3 microfarad and 6 microfarad. 2, 3, 6. They are connected in series. First we have to calculate the effective capacitance of the combination. So because it's a series combination, we just need to use the series combination formula. 1 upon 2 plus 1 upon 3 plus 1 upon 6. LCM is 6. So 3 to the 6 plus 3 to the 6 plus 6 1 the 6. So 3 plus 2 5 plus 1 6, 6 by 6, that is 1. So C equivalent is also equals to 1. Okay, so this is the equivalent capacitance. First part done. Second part is find the potential difference across 6 microfarad capacitor if the combination is connected to a 60 volt supply. So this capacitor is connected across a 60 volt supply and you are asked to find the potential difference across this one, say V. Now remember that in say V dash, remember that in case of series combination the charge passing through each capacitor remains same. So each capacitor gets to charge by the same amount. In case of parallel combination, voltage remains same. In series combination, the current or charge remains same. Okay, in case of resistance, current. In case of capacitor, current is not super important, charge is more important because charge is current into time. So we can say charge remains same. Now if you consider the equivalent circuit, if you consider the equivalent circuit should also have the same charge. Okay, so this is the C equivalent, this should also have the same charge. Voltage is again same. Okay, charge should also be same for equivalent circuit which has a capacitance 1 microfarad. So we will use that 1 microfarad to find the charge. So how to do that? Q equals to C equivalent into V. So this is the voltage, original voltage. Okay, the same voltage is across C equivalent. Okay, C equivalent is 1 microfarad. 1 microfarad means 1 into 10 to the power of minus 6. Voltage is 60. So we get 60 into 10 to the power of minus 6 coulomb. So this is the charge that is passing through each and every one of the capacitors. So same charge will pass through the 6 microfarad as well. Now if this voltage is V1, charge passing through this is Q, then again we can write Q equals to 6 microfarad into V dash. Okay, this V dash we will find. Q we have calculated, 60 into 10 to the power of minus 6 equals to 6 into 10 to the power of minus 6 into V dash. Okay, 10 to the power minus 6 cancels, we get V dash equals to 10 volt. So V dash is 10 volt, equivalent is 1 microfarad. Now in first part is easy, second part is, sir, first I found U1 equals to 9 into 10 to the power of minus 8 joules, U square is 18 into 10 to the minus joule, and then find the work done. Yes, correct. Yes, 9 into 10 to the power, yes, 9 into 10 to the power minus 8 can be written as, if you see that here, 9 into 10 to the power of minus 8 can be written as 90 into 10 to the power of minus 9. Why I have used this? Because it is basically, normally unit is joules, but 10 to the power of 9 can be shortened to nanojoules. Okay, that's why when you are using large unit, minus 10, minus especially negative values, minus 9, minus 10, minus 11, minus 12, try to reduce it if possible. Nanojoules, microjoules, okay, or picojoules in some cases. Okay, same problem, same case. Remember, final position minus initial position. Initially it was at 0.2 meter at a distance. Final is 1.1 meter distance. So that means, and because the total energy of the system is negative, your work done is also negative. Okay. High excess jai. And Pradyum, check your U1. U1 should also be negative. U1 should also be negative. You have written minus 18 for U2, but U1 you have written plus 9 into minus 10 to the power of minus 18. So U1 should also be negative. And as I mentioned, this is a thing that you have to understand, that how can you shorten the length of the calculations. If you start putting, if you put everything in your calculator, it will be very long calculation, you will not be able to manage it. So stop using calculators from the beginning. I have seen students, they use individual terms using calculator and then add it. That is the wrong method. Try to simplify first, okay, in terms of variables, then take commons, whatever is possible to take common, then you use your calculator. In fact, this problem does not require calculator to solve. Now, formula sheet for the chapter. The charge, change in potential equals to work done. Change in potential equals to work done. Potential due to a point charge is given by V equals to 1 by 4 pi epsilon naught Q upon R. Potential in difference in potential energy divided by unit charge is the difference in potential, and also it is the difference in potential for between 2 points. V equals to VB for A tends to infinity. So if you take one charge at infinity and bring it back, you get the potential for a point, and this is the comparison graph of voltage and electric field. Now potential energy of two charges is given by U equals to 1 by 4 pi epsilon naught Q1 Q2 by R. Three charges is given by 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q1 Q2 Q3 by R23. E equals to dV by dx, and polarization formula is P equals to epsilon naught x E and its dimension, polarization dimension is L to the power of minus 2 A into T. So everything at one place. 2-page formula sheet. Parallel plate capacitor, capacitance is given by normal, in general it is given by K A epsilon naught by D. K is capital. Okay. K is capital. Q equals to CV. Series combination, 1 by C equivalent equals to 1 by C1 plus 1 by C2 plus 1 by C3. For two capacitors, C1 C2 by C1 plus C2. Okay, parallel combination, V is constant, C equivalent C1 plus C2 plus C3. Now if n number of capacitors of capacitance C are in series, then equivalent capacitance is C by n. In parallel it becomes n into C. These are all handy for your KCET exam. Energy stored half CV square, half Q into V, half Q square by C. Energy density is half epsilon naught E square. So these are all the important formulas from the chapter. And if you want to download the lecture PDF, don't forget to join our WhatsApp channel. The link is given in the description of this video. The lecture notes will be shared after this lecture is over in our WhatsApp channel. The link, download link will be shared. Okay. Now practice question, we will practice few questions. I will give you some time to solve. If you are interested, solve it. I will give you 2 minutes per question. I will solve 1, 3 and 5, 2 and 4 will be homework. So you have to solve it once you download the PDF. Okay. First question for everyone. Try to solve. Particle A has charge plus Q and particle B has charge plus 4Q, each of them having the same mass, capital small m. When allowed to fall from rest through the same electric potential, the difference, same potential difference, the ratio of their speeds will be. So let me help you. So we have electric field, some electric field. Okay, the charges are allowed to fall through the electric field. Suppose the electric field obviously in this direction, no gravitation by the way. Gravitation, we are not considering any gravity. We are only considering electric field. Even though mass is given, gravity is not being considered. So this is the electric field. You have a charge plus Q, you have a charge plus 4Q, and you are allowed them to fall through this electric field. Okay, only electric field is there. So after okay, potential difference is same, obviously same potential difference. Once it is coming out of the electric field, what is the ratio of their velocities or speed? Hello my lamp, you are late today. Our lecture is almost over. We are just solving some practice questions. Try to solve. The entire lecture is over, but anyway you can check that out once. Today we do not had too many distractions, so lecture was almost perfect. So you can check it anytime if you want, and do not miss the lecture. By the way, lecture is very important. Even if you have not, Pradyum is saying option B 1:2. Let's see. So particle has charge plus Q and particle B has charge plus 4Q, each of them having same mass V. When allowed to fall from the rest through the same electrical potential difference, so say potential difference say dV, potential difference say dV, the distance say dx. So what we know, the magnitude of electric field is given by dV by dx. Okay, magnitude of potential difference is dV by dx. So what is the force acting on the first charge? Force acting on the first charge is given by Q into E. Force acting on the first charge is Q into E. Force acting on the second charge is plus 4Q into E. Forces are different. Now what is the acceleration of this charge? Or what we can say, let's not go into this way. We have one more interesting easy way. Potential difference is given, no? So what we can say is that, what is the work done? What is the work done when this charge crosses this potential dV? The work done is given by, so work done say 1 equals to Q into dV for first charge. Okay, so and we know that this same work done will be converted into its kinetic energy. So half m V1 square. So from here we can calculate V1 equals to 2Q dV by m whole root. Similarly, V2 can be calculated 2 into 4Q dV divided by m. Very simple. So whatever work done is done, when it is passing through the potential difference, the same will be converted into kinetic energy. Okay, so work done equals to kinetic energy, work energy principle, and from there we can calculate. Okay, so V2 will be 2 into square root of 2 into Q dV. So we have taken the square root of this 4, remaining we have not changed. Okay, why? Because this is exactly same as V1, so V2 equals to 2V1. Okay, so ratio of their speeds, so V1 is to V2 equals to 1 by 2, so 1:2 is correct answer. Yes, option B is correct. Pradyum is correct. My lamp is also correct. Okay, Both of you are correct. Now, question number 2 is homework. Solve it on your own. Very interesting question. If you are not able to solve it, once the live is over, download the PDF and try to solve this very interesting question. If you are not able to solve it, mention in the comment below. I will try to provide a PDF link for this solution. Otherwise, try to solve it. Okay, don't take any help. Try to solve it on your own first. Question number 3. A parallel plate capacitor has a capacity C. The separation between the plate is doubled and the dielectric medium is inserted between the plates. If the capacity is 3C, then the dielectric constant of the medium will be. So initially only air was there, so it was epsilon naught A upon D. Now what you have done, you have initially this was the capacitor. You have increased the distance now to double the distance. You have doubled the distance and inserted a dielectric medium, say K. So dielectric medium is inserted as well as distance is doubled. So what will be the dielectric constant K? You have to calculate the dielectric constant K. Solve it quickly. Quickly. Okay. Yes, correct. Easy question. So C equals to epsilon naught. Question number 2 was difficult, by the way. So that you have to solve on your own. You have to practice little bit more difficult question after you have completed the chapter. So C equals to epsilon naught A by D and 3C equals to K epsilon naught A divided by 2D. Okay, you have to calculate this K. So K by 2 into epsilon naught A by D. What is this? This is same as this capacitance. So we can say that this is K by 2 into C. So 3C equals to K by 2C. C cancels and K equals to 3 into 2, that is 6. So answer is option C, 6. Okay. Pradyum is also saying 3C, correct. Now, this is also another question. This requires a concept which I will give you a hint. Look into the structure of this. Okay, very common structure. If you can find out what structure it is, you will be able to solve it. Okay. Now, next question number 5. The region between the parallel plates. This question will be available if you want to download once you download the PDF. Okay, download the PDF, solve these questions and let me know the answer in the comment. Both question number 2 and question number 4, practice questions. Mention the answer in the comment section. The region between the parallel plates of capacitor is filled with parallel layers of air and paper of dielectric constant 4. The space between the plates is 1 millimeter and the thickness of the paper is 0.75 millimeter. The ratio of voltages across air and paper is. Very interesting question. So region between the parallel plate capacitor, we have a parallel plate capacitor. Let me draw the diagram for you. Parallel plate capacitor is filled with parallel layers of air and paper. So we have layer of air as well as layer of paper. Okay, the space between the plate is 1 millimeter. So the space is 1 millimeter and the thickness of the paper is 0.75. The thickness of the paper is only 0.75. So basically this much is paper and this much is air. This is air, this is paper. Okay, now they are asking that the ratio of voltages across the air and paper. The dielectric constant for this is K equals to 4. You have to find the ratio of voltages. The voltage is not given, by the way. So if you are wondering how to do that, you know that Q equals to C1 V1. Charges will be same. Both will have same charge. Charges will be same, voltages will be different, capacitance will be different, and you have to find the ratio. Okay, so V1 by V2 is basically C2 by C1 from here. I will explain it a little bit more if you are not able to solve it. Question number 5, guys, quickly. Confused? Okay. I'll tell you the secret. So first of all, what you can understand is that here we have, if you instead of thinking it like a single capacitor, what you can do is consider this to be two capacitors in series. Now it will be easier for you. So we have two capacitors in series. One is air, another one is paper. Thickness of the paper is 0.75, so no doubt about it. So whenever you see the questions like them, that one capacitor half is filled with one medium, dielectric medium, second one is filled with another dielectric medium or empty. So you should remember that because it is done like this, you can separate these two into two separate capacitors. One is this one, another one is the other one, and they are connected in series. So this is a combination of series. There is in another case, if they are filled like this, then it can take them as parallel. Okay, this concept is important for JEE, not so super for KCET. Okay, maybe for Comet K, but not for KCET or PU Board. Obviously not for PU Board. KCET level generally this concept is coming. Okay, so here you have to just consider them to be series combination. Even series combination is not required. Only you need to know they are two different capacitors. One is C1, this one is C2. If you can calculate their capacitances, ratio, you just need to find the ratio. Okay, this one is clear, right? So if both of them are connected in series, so charges will be same. Charges will be same. This one is paper, this one is air. So total length was 1 millimeter. Out of that, paper one is occupying 0.75 millimeter. So remaining 0.25 millimeter must be air. Okay, total length was 1 millimeter, 0.75 goes to paper. So remaining 0.25 must be for air. So air, the thickness or distance in case of air is 0.25. If you understand this much, the problem is solved. So this is C1, this is C2. So what is C1? C1 has only air. So epsilon naught A upon distance D1. Area is constant. Both capacitors should have same area. Both capacitors should have same area. Area is not changing, only distance is changing. So what is this? 0.25. And we will not even consider the units. Units are also not important because ultimately you have to find the ratio. So units are also not important. So epsilon naught A divided by D1. D1 is 0.25. What is 0.25? 0.25 means 1 upon 4. 0.25 means 1 upon 4. 0.75 means 3 upon 4. And 1 upon 4 is in division. So epsilon naught A divided by 1 upon 4. So this 4 will go up. So C1 you get 4 into epsilon naught A. And this is C1. What about C2? C2 has not only the distance is different, but also it is a dielectric medium of dielectric constant 4. So in this formula we have to use K epsilon naught A upon D2. Okay, so it will be K is given 4, epsilon naught is constant, A is given constant, distance here is 3 by 4. 0.75 means 3 by 4. Now do the multiplication, you get 16 by 3. 16 by 3 epsilon naught A. Okay, 16 by 3 epsilon naught by A, and we already know that Q equals to CV, C1, so Q is equal to C1 V1 and Q2 is equal to C2 V2. So if you want to find the ratio of their voltages, you have to take the reverse order. Okay, so from this formula you can say V1 equals to Q by C1, V2 equals to Q by C2. Okay, charges are same, so ratio will be reverse. So V1 by V2 equals to C2, that is 16 by 3, divided by C1, that is 4. Okay, epsilon naught A is constant, so they get cancelled. So we get 4 by 3. So the correct answer is 4 by 3. Correct? Yes, Mylam answered it. Pradyum got it? Understood the problem? How to solve, how to tackle these kind of questions? Okay. Question number 2 is based on this, how you separate different dielectric mediums into 2 different or 3 different capacitors. Okay, so this is very common. If suppose you are given that one capacitor is filled with 3 different dielectric slabs of different thicknesses. Okay, so you can take this one as capacitance C1, this one capacitance C2, this one capacitance C3. Okay, so these are all 3 capacitors connected in series. So you calculate their individual capacitances and then add them. In KCET level, the calculations will be easy. Only thing you have to remember, you have to consider the respective distances. Distances will be different, D1, D2, D3, and the dielectric medium constants will be also different. So this is a hint for your problem number 2. Problem number 2 is based on this concept. Okay, right? So this is the end of this lecture. Okay, so if you have any more doubts, any more questions, don't forget to mention in the comment section of this lecture. And also I request you solve and post your answers for practice question 2 and 4. Okay, 2 and 4 practice questions, solve and post in the comment. Okay, thank you guys, thank you for watching this lecture, thank you for being with me for so long. I'll be back with the PUC pre-board preparation next week, and after that we will be resume this series with current electricity. So be patient. Pre-board is also important, don't miss out on that. Pre-board preparation will happen next week, and after the pre-board exams are over, mid of next week, we will resume with current electricity and moving charges and magnetism. Okay, till then, bye, see you soon.